Really pleasure to be on Korea. Let me say only one sentence about, since we were at the Polish affair, that Poland is something in many things similar to Korea. We got independence in 1918, a couple of months before Korea got independence. In 19th century we were occupied, split between Germany and Russia. And we have two big neighbors like you in China, Japan, Germany and Russia. So it's everything I wanted to say about the history. Now I'm going to say about this subject. This is a joint work with Felek Przytycki, who is and now he had been elected just in the spring the director of Mathematical Institute of Polish Academy of Science. And what is about? It's about a notion of topological entropy. I will explain you what is this. And it confirms so-called entropy conjecture for self-maps of chi-pi1 manifold. I assume that you know what is chi-pi1 manifold. Is a manifold, compact manifold, such that the fundamental group is equal to a given, pi group, and the remaining homotopy group vanish. So there is no other homotopy groups. An example is the torus. You have a fundamental group equal to classical torus Z times Z, and d-dimensional is a Z to the power d. Okay, so it is known, and it is basic homotopy algebraic topology, that self-maps of such a manifold, which is k-pi1 manifolds, are from homotopy point of view well controlled. Namely, homotopy classes of maps from M to M are in 1-1 correspondence with homomorphism of this group pi. So if you know that the map induced by a given small f is a homomorphism, then every map f prime which has the same map induced on the fundamental group is homotopic to a given f. The converse is obvious. So our point of view will be group theoretical in the sense that I would not look at the map f as a map, but I could look at the map as a homomorphism of pi1, because this homomorphism determines the homotopy class of f. And the program, or the aim, is to find out a numeric invariant, a number, real number, which estimate topological entropy. I will explain what is this topological entropy from below, and which is homotopy invariant, and we have this inequality. This is important because one notion, namely this invariant, could be constructed in purely homotopy algebraic topology way, namely it's homotopy invariant, but topological entropy is not a homotopy invariant. It is not continuous in C0 topology, namely in this sense that if you have a map and you change a little bit by small perturbation, so small perturbation of self-map of a manifold is homotopic. But it could have completely different topological entropy. So if you change a little bit your map, topological entropy could change drastically. And I will give also examples. Now let's go to the definition. Definition of topological entropy is written here. It measures dynamical complexity of a given map in the following way. Let me make this, or show you in different words this definition. Suppose that in your manifold you have a matrix rho, then fixing epsilon and n, a natural number, you could introduce a metric, which depends on n and depends on f2, and the distance between 2 points is a maximum over distances of the points, consecutive points of a trajectory. So you have 2 points, x, y, then you take f of x and f of y, and then you take f2 of x, f2 of y, and you measure distance, this distance, this distance, and this distance, up to n minus 1, and look which is the largest. And this is your new distance between x and y. And one can check that this is really metric in this space. And if you have an epsilon, then for the compact space and a metric, there exists a smaller number of epsilon isolated points with respect to this metric. So if you take more than this number, then there are 2 points which are in distance smaller than epsilon. For example, if you have an interval 0, 1, and epsilon is 1/3, then the minimal is 3, because if you take 4 points, then 2 of them has to be in the distance smaller than 1/3. And this is our Q with a fixed epsilon and n. And then you take a limit, this is upper limit of this quantity, this is logarithm, and divided by 1/n. And this is a first step. The next step is you pass with epsilon to 0. One can easily show that this function is monotonic decreasing function of epsilon. So if you measure epsilon smaller and smaller, then the quantity without this epsilon would be larger and larger, no smaller. So this limit as a limit of positive and monotonic sequence always exists. Could be infinity as well, but why not? And this is called topological entropy. So the measure, so in some sense it's topological. If it's big, it means that the dynamics of F is complicated. The trajectory are mixing a lot. But if your map F is preserved distance, or it's not expansive, this is an exercise to you. So it doesn't expand the distance, then it is easy to check that this is equal to 0. Because here, if you look at trajectories, this is the maximal distance. Here it's smaller and smaller. So always you have the same quantity. You divide by 1/n, and you go to infinity, so constant by n tends to 0. And then it's not important epsilon, because for every epsilon you have 0 as a first limit, so limits of 0 gives you a 0. Okay. So it was introduced by Poznan in 60s, and it has, now there are many definitions. One is very similar to the classical definition of a metric entropy due to the Arnold. What I wanted to show is this guy, dynamical guy, is not C0 in continuous, namely this is example which we called Shoup example, used by Shoup. Namely, suppose we have a sphere. The Earth here is North Pole, South Pole, and we consider a map which along each equator is z to the power. We can identify each equator with a unit circle of a complex number. And this is z to the power r, where r is whatever, it could be very big. But it's not enough. If we take only this, it would be suspension of z to the power r. But we move a little bit each equator in this direction from south to north. Here very small, here bigger, and here once more very small. And this, you obtain an image that everything is moving from the south to the north, and simultaneously here is doubling or flipping. And how many periodic points you have? Only 2 fixed points, because everything goes. And this map, which let it be F, has entropy, topological entropy. By some theorems, one can show that it's equal to 0, but this is a map of degree r, where r is this r, because it's homotopic to the suspension, which has degree equal to r. And American mathematician Michael Shoup in the 70s posed the question, under which assumption we have this inequality, where on the left-hand side we have logarithm of a spectral radius. Should I explain what is this of f? Namely, f induces a map on the cohomology. One can take homology as well, but for some reasons cohomology is better, with real coefficients. This is finite dimensional real space. This is finite dimensional self-map. So this is finite dimensional linear map, a matrix. Obviously some big size, but a matrix. So it has a spectral radius. Spectral radius, you had been told during the linear algebra, it could be identified with the largest absolute value of an eigenvalue belonging to the spectrum. So, or it could, there is another definition, but and so on the left-hand side we have this logarithm of a spectral radius in this meaning. Look, this is topological functor, so it's homotopy invariant on the left-hand side. On the right-hand side, we have topological entropy, which is, if you perturb a little bit just suspension, you get here 0, and for this map, the logarithm of spectral radius is exactly, dec f is equal to r, is equal to logarithm of r, so r could be as big as you wish, not only 2, but let me say million and so on. So we see that for continuous maps and any manifold, entropy conjecture is not true. There is counterexample. And Shoup asked about the assumptions under which it is true. This map, by the way, is not here, is not smooth, and cannot be smooth. Here is smooth. So, what was historically proved, I only mentioned the main results. To Misiurewicz and Przytycki, the same Przytycki, they proved in the late 70s that if you look not at all cohomology space, but only on the highest dimensional part, so this is a part, degree, and your map is C1, it's okay. So you have partial. If you look at what is going on the first homology or cohomology, because they are dual, it's also okay, even for C0 continuous maps. This is due result of Manning, also Anthony Manning, British mathematician, in 70s. The complete entropy conjecture had been confirmed in such a complete form by Israel mathematician originally from Soviet Union, Yovnin, in late 80s, but under very strong assumption on the map, C infinity. And the proof cannot be adapted to any ck with a k finite. So it's C infinity. But on the other hand, the same time, there are two papers, one consecutive paper in Bulletin of Polish Academy of Science. It was observed that if your manifold is very special, namely is a torus, you could get rid of the assumption of smoothness, which is necessary in general. Namely, it's true for any C0 map. C0 means continuous. For topologies, it's for any map. But here it's a problem. And what we, with Felek, had done, we made a step forward, so-called Katok version of the entropy conjecture, which says that if the manifold is good, if it's k pi 1 and the universal cover is homomorphic to the Euclidean space, like for the torus, then you have the EC, entropy conjecture, for any continuous map. Why we did next step? Because we prove it for Nil manifolds, compact Nil manifolds, and in these papers I'm going to present for infra-Nil manifolds, or for manifolds which are finally covered by Nil manifolds. It's a little bit larger class, and during the 30 years there was nothing done in this direction. Okay, so I don't know how much do you know about Nil manifolds and infra-Nil manifolds. So this is a problem, because it's a language. If you don't know language, I mean, then everything is it's abstract, not understandable. But let me just mention that it is connected with algebra. If somebody is interested in algebra, in, for example, geometric group theory, then there is a notion of growth of a homomorphism, or growth of the length of a word in a group, which is finitely generated, which is defined here. So you express your element in all possible ways by generators, and take this as a measure, and then you iterate your homomorphism, and you get some number, which is, you see, the same logarithm rate of growth of a sequence of numbers which are obtained in this algebraic way. And this was already used in this proof of Manning, that this expression this is algebra, and if we put as a pi fundamental group of a given manifold, then this algebraic thing estimate from below topological entropy. So in some sense, logarithmic growth, rate of growth on the fundamental group is good for the estimate of topological entropy, but if it's good for the fundamental group, it also is good if we consider its abelianization, which is the first homology group, and then more or less you obtain, of course it's not so easy, the Manning theorem I have already mentioned. Okay, so here there are definitions, but probably I have to give you definition of Near manifold, starting from the definition of nilpotent group. Nilpotent group is defined in algebra in the following way. We say that gamma is nilpotent if we consider the following sequence of its subgroups. The first one is commutator. The second one is commutator of the first with group itself, and so on. So each time, since this is smaller than gamma, you obtain something smaller, smaller. And if it finished, and here, see, n minus 1 and gamma n is equal to the trivial group, then group gamma is called nilpotent group, a nilpotent group. Of course, abelian group is nilpotent because you can take just, here is the last, first is the last. And what is known that, let me say, what is Near manifold? Suppose that you have a nilpotent connected, simply connected. Simply connected means that its fundamental group is trivial. Lie group, and gamma is discrete subgroup such that the quotient is compact, then this quotient is Near manifold by the definition. It's a more general definition, but let me say general case reduces to this by Marzantowicz theorem, so one can think about Near manifolds as such a homogeneous spaces. The simple example is you divide Euclidean space by the lattice and you obtain the torus. But this is abelian, so it's not interesting. One can ask why consider the theory of Near manifolds if the only one example is the torus or our tori. The non-trivial Near manifold appears first in dimension 3. Up to dimension 2 there are only torus and one is circle. Namely, look, if you write down the following matrices, B, C, with the real coefficients, they form a group with multiplication because every matrix is invertible. The determinant is equal to 1. So this is a continuous subgroup of GL3. But it has its discrete subgroup consisting of all matrices with n and k integers. So if you divide this previous subgroup, continuous group, Lie group, by this discrete subgroup, you obtain something compact. So this is just, one can check that. And this is called Heisenberg Near manifold, or baby Near by Americans because they don't like this Heisenberg. And it is not three-dimensional torus. It forms a fibration with a base equal to the torus and the fiber, the circle. And truly speaking, if here you take denominators, R you obtain with different R, not isomorphic, so you have infinitely many not diffeomorphic Near manifolds. But for the beginning, let's take R equal to 1. So now you have examples. And infranil, it is interesting because this is a class which strictly in the definition of this class had been introduced by Korean mathematician K.B. Lee. I mean, could consider him American or Korean, it depends.
Only Korean is always Korean.
No, in Polish culture we consider self-declaration as a yeah, so if somebody considers himself as a German, yeah.
He didn't get the citizenship, American citizenship. He has only green card. So he declared his Korean.
I believe you, but this is more of I wanted to because in Germany it's the rule that if your parents are German blood, then you are adopted automatically by them. In France, if you are born in France, so if you are of Arabic origin or African, but you are born in Paris or your kids, so it's automatically French. Yeah. Okay. So KB, and one can think that there are finite covers. It's a larger class, but finite covers of being finitely covered by Near manifolds. So the good example, the first one is the Klein bottle, which is double covered by the torus. Torus itself is Near manifold, trivial abelian. Klein bottle is not, because it's dimension 2. So no examples of Near manifolds, but it is infranil manifold. So this extension in some sense essential. Okay, let's go to the next. And what we proved, here I am not going. So we proved for the class, which, as I said, it is not exactly, and there are some technical, behind these technicalities there are very deep mathematical theorems, but at the beginning even we were thinking that these two classes are equal. Namely, we consider K pi 1 manifolds with pi of the following form. So you have gamma, which is normal subgroup of your pi, and here, and it is of index, of finite index, so it means the quotient is a group because it's normal, and additionally it is finite index, so this is finite, and gamma is nilpotent. Infranil, in its formal definition, they are subgroups of this twisted product of this GG's, the continuous nilpotent Lie group, and C is a compact, maximal compact subgroup of its automorphism. So whatever. It is a little bit more difficult, but it's more constructive. So we reduce it in some sense topologically, our case, to that one, which is the definition of infranil introduced, used, and described by KB Lee, not KB Lee, and the essential step in our proof, and also essential in the definition of the invariant, is the fact that every self-map of infra-Nil manifold is homotopic to very nice map, namely to an affine map. This is the main theorem of Lee in his paper. He introduced it. This is corresponding to the following fact, that if you have a torus and you have a continuous map of a torus, it is homotopic to a map which is induced by an integral matrix. And if you have the Nil manifold, this is the same, but we instead of integral matrix, you have to consider a homomorphy preserving the lattice. So factor of homomorphism. Here is not enough factor of homomorphism. You have to add a translation small b, which means that you have to work with affine maps. But if, this is techniques, but if we have these techniques, one can define something which for this b is a rotation part, this is orthogonal. It's a homomorphism of this group G. So we can take derivative it in the unit element, and we obtain an endomorphism of Lie algebra, linear map. This linear map has its spectrum, and also we can consider the full exterior power, consisting of all exterior power of this map. And then we have something which is more larger, richer. It has it's also its spectral radius, which is equal to this. You have to take multiplicity of all eigenvalues of original df, which are up to module greater than 1. And this is spectral radius of this. And in general, it is larger than spectral radius of the F itself. And our theorem says, that for continuous self-map of a compact manifold, which is K-pi1 space, with a group pi virtually nilpotent, this is the definition here, we can estimate topological entropy by this invariant, log or spectral radius of this full exterior power of linear map, some linear map, and one can easily prove that this is larger than spectral radius of a map induced on cohomology. Even there are examples due to Smale described before, in which it is sharp inequality. So, moreover, these nice affine maps, which we use it as a representative of homotopy classes, they have minimalization property. Namely, entropy of them is the smallest in each homotopy classes. So, for example, for the torus, the linear maps have the smallest entropy in the homotopy classes, in the homotopy class. So, and everything, in some sense, we get rid a language, because this guy could be defined in the purely group, fundamental group theory terms. It was in here, but let me say, skipped it. We get rid of manifolds, and everything is formulated in the language of groups only, fundamental group only, which was suggested by Michael Schub. So it is an advantage of this approach. But the main step of this theorem had been done previously in the previous paper, when we proved by dynamical methods that this same holds for the self-map of compact Nil manifold. And what was game here was only with generalization and carrying up our result into the infra-Nil, or to this from. Okay. So these are these difficult facts, not trivial facts on algebraic topology. Here, when it was written, there was a gap in dimension 3, which is now filled because Thurston geometrization conjecture had been proved, so it's okay. But we had another proof, so it doesn't. Let me say, topological, easy but essential steps to pass from the estimate for a self-map of nil manifold to the self-map of infranil, so go down in the cover, is contained in two facts. Namely, first one, very classical, is that if you have a situation, you have a map, you have a commutative diagram, and M is above and M hash is above and M is, so it's like this. Then topological entropy, and here is a finite cover, then topological entropy of this map is equal to topological entropy of that map. It was known, even there is a...
Finite cover or for every cover?
If you have every continuous map, you have inequality that topological entropy of this is greater or equal to. But if your map
any covering space,
any covering, or even for any p, for any continuous map,
for any?
Maybe not for any, but much more general assumption works this inequality. I don't want to because I could go.
That's really true for covering space.
Yes, I think that's onto. The map has to be onto surjection. You have this inequality, but if there's a finite cover, you have equality. And it was known classically. And second, which is something which let me say, for me was obvious from the finite group actions, namely that the spectrum of this map is only a part of a spectrum of that map. Because if you look at the real homology space is the cohomology of an orbit space. Here there is a free action. It's a fixed point set of action on homology of a space itself. So you have only a part of this is a part of this matrix, subspace, and this spectral radius of a linear map on the subspace preserved by it is smaller than on the general, because you have more eigenvalues, so it's, in some sense it's very easy. Okay, and to get applications, I will use 3 minutes more. One can employ classical results on the number theory. Namely, in the number theory, there is a classical notion of Mahler measure, which is defined here. You have a polynomial, and there is a definition. You take multiply of all roots of a given polynomial, which doesn't contain cyclotomic polynomial. And extra you have to multiply by the leading coefficient. And this is Mahler measure, and Lenner conjecture says that this expression is estimated from below by some constant, which doesn't depend on the polynomial. Absolutely. Which is very difficult, long-standing conjecture on number theory, but it has partial solutions. Namely, if you don't mind any, but you ask, is it possible to estimate where C depends not on polynomial but on its degree, then it's true. And the best result is du Vautier, which works not asymptotically but works for NAD, says that this Malor measure is greater or equal than right-hand side expression, which doesn't depend on the polynomial, only on its degree. So if we have this result, we can say, using our theorem, look that this multiply is exactly spectral radius of the characteristic polynomial of a matrix. Not of a matrix, but of the full exterior power. We have an expression in which the spectral radius of the full exterior powers is exactly the multiply of all eigenvalues which are greater than 1 up to absolute value. So what is equal or smaller up to absolute value, you don't count. So if you have this, you get the following. If you have a continuous map of a confound infranil manifold, then the topological entropy either is equal to 0, but if it's not 0, there is a gap. It is greater than logarithm of this tau of D, which doesn't depend on F, only on D, and you have arithmetic expression. And this, moreover, there are some polynomials for which the Lemmer conjecture had been confirmed completely, and they are so-called no reciprocal. Reciprocal is the following, that you have polynomial, and instead of polynomial in the variable lambda, you substitute lambda to the -1. And if this new polynomial has the same zeros, then it's reciprocal. So for our theory, or for Smith's theorem, they are not good reciprocal. So substituting instead of lambda to -1 should produce new zeros of the new polynomial. So the theorem of Smith says that if polynomial is not reciprocal, then the Lemmer conjecture is true. So if it's true, okay, we can apply to our stuff, and we get the following, that if we know from something that our matrix, which we define, let me say I only said but did not define, then, and we know that there is not 0, but we have greater than 0, then it has to be greater or equal than these constants, which these constants now doesn't depend on dimension. So it's absolutely, and this is numeric value, and it can be applied to, if you know what is Anosov automorphism. So if you have an infranil manifold, there is another conjecture that there are no other manifolds than infranil manifolds for which you can construct an Anosov diffeomorphism. So, but this is another conjecture. So considering Anosov diffeomorphism on infranil manifolds is nothing artificial. It's, and so if you have an Anosov automorphism diffeomorphism such that the unstable subspace has dimension different than stable subspace, we just get the assumption of our theorem, and we know then that every map which is homotopic to Anosov automorphism has topological entropy either 0 or greater than, like here. So I think my time is over, so I would like to stop. Thank you very much.